it's a privilege being here. We've heard quite a lot about very complex system. Now we go to the other extreme. So the most simplistic creatures you can imagine on the earth are bacteria, as you know, and they are all over the globe. They can really feel all the possible niches, even the most extreme environmental conditions. And pretty much antibiotics are very tiny molecules, which actually mostly are effective against some of the most dangerous bacterial pathogens. And they have been used for ages. And now what we are facing is that they are less effective at the moment. So you may have heard in the news pretty recently that now we are facing another antibiotic crisis, and there it's been all over across the press, even in the Hungarian newspapers. And it's already antibiotic resistance in these dangerous pathogens is one of the leading cause of death in the third world countries. But as a matter of fact, it is actually reaching us, according to some pessimistic estimates. And for the very first time, it may actually happen that the life expectancy in Western societies will decrease due to these antibiotic-resistant pathogenic bacteria. So, as you all know, some of the bacteria are actually very good for us. They are helping us to digest food and so many other things, but there are quite a few other, we have quite a few enemies. And this figure just shows some of these enemies which are all around us, and they are increasing in portion, and they are becoming resistant to some of these most dangerous, to some of these antibiotics we are using. Just to get a rough estimate, here's a very simple slide. Vancomycin is now used for some of these dangerous pathogens, as you can see, over the years, the percentage of bacteria resistant to this antibiotic has been increasing at an alarmingly high rate. And this is actually not just one example, but it's actually ongoing. So quite for a while now. So if I may put it that way, there's an arms race between the human and these rapidly evolving pathogens. So let's just say, for example, in the case of Staphylococcus, first they used the classic antibiotic penicillin for ages, and then now they are becoming resistant, so they have to find new treatment, new antibiotics. So then methicillin, another antibiotic, reached the market, and in 20 years of time, it's becoming ineffective again, and again and again. So constantly we are facing new pathogens, and we have to develop new antibiotics to treat these infections. And some of them are actually pretty dangerous. So there's actually something really bad going on here, because on one hand, there's an alarmingly higher rate of these antibiotic-resistant bacteria, but secondly, the market of producing a new antibiotic is actually decreasing. Because let's think about with the head of an investor. If you put $100 million or more into development of a new molecules and it will be ineffective in a few years' time, then there will be no profit at all, right? So what's the point of investing this huge amount of money in that? So that's what we actually have been seeing during the 1990s and 2000s, that there have been less and less antibiotics reaching the market. Slowly but progressively, this trend is changing, so now we are in a better shape now. So there are many different new, potentially good antibiotics reaching the market. We will see how it goes, but the trend was very clear during the end of 90s and of 2000s. So why do we see antibiotic resistance at all? We should blame us. It's all possible. Firstly and foremostly, it's due to the absolute overuse of antibiotics, let it be in the clinics or in the or basically in livestock and fish farming. So basically, and also for preventive usage when there's absolutely no reason to use them. So we are, the humans in general, generating an enormous selection pressure to select for these resistant bacteria to emerge and spread across the globe. So as I said, there's an uncontrolled antibiotic consumption. There's roughly 500,000 tons annually consumed, let alone in China. And it's been used, as I said, also in agriculture and in the clinics as well. And probably the biggest danger is not the consumption in agriculture, in the clinics, but actually in the clinic, in the agriculture. So we can say that there's a huge overusage of these antibiotics, leading to the state that 50% of the dairy products, like milk in China, are contaminated with antibiotic, right? So if that's the case, then it turns out that wherever these bacteria are, they will have enormous potential to reach antibiotic resistance because the selection pressure is there, antibiotics are there. So in case of the animals can carry harmful bacteria in their intestines, in their gut, and if we treat them with antibiotics for preventive usage, which is more or less the case and then antibiotics kill most of the bacteria, but we leave these resistant bacteria to multiply and survive. And as a matter of fact, in the long term, we can consume these bacteria and they will spread to human population. That's a potential danger. We don't know how realistic this danger is, but clearly the potential is there. So how bacteria becoming resistant to antibiotics? As a matter of fact, antibiotic resistance is an enormously rapidly progressing evolutionary process. So there are two major ways of doing it. One of them is basically random mutations in the DNA of the bug, and if there's a specific mutation that will increase the likelihood that they become resistant, they will spread in the population. But as you will see, they do not have to reinvent the wheel. In certain cases, they just actually acquire DNA from other species which provide these resistant mechanisms. And last but not least, another problem we have with antibiotics is that they are generally not selective enough. As I just said, there are good and bad bacteria alike, and especially in the gut, there's a microbiome, hundreds of bacterial species that will help you to digest your food. And when you are treated with antibiotics, generally it doesn't only kill the pathogens, but also it will have an immense effect on your microbiome, on the healthy bacteria. So quite frankly, we need some other treatments and antibiotics that will be far more selective than the current ones. It's easy to say, but far more difficult to actually work it out. So how does resistance actually work in the case of mutation? There are some replication errors in the bacteria population, and given that they are so tiny and they multiply in a very rapid manner, then there's huge population. Such mutation will actually arise in a very rapid manner in terms of weeks, if you like. And if such resistant mutation arises and there's an antibiotic treatment, only the mutants that confer the given resistant mutation will able to survive and they will spread in the population. Usually you see multiple mutations which are needed to reach a high level of resistance. So that's a kind of hope because it decreases the likelihood that they will emerge simultaneously. But as I said, that's only one of the ways they gain resistance. The other is actually, this is pretty nasty. So they've got a dirty trick that eukaryotes and humans don't actually have, is that they can gain antibiotic-resistant genes through a mechanism which is called horizontal gene transfer. And in a nutshell, it's basically gaining DNA fragments from other species. So let's just say that one bacteria invents a new mechanism for resistance in their genome, or in a given plasmid, so then it's not necessarily the bacteria per se that would spread across the globe, but only the plasmid that carries the resistant mechanism. And this is actually what's happening. There is a new resistant mechanism arising in India, and in 10 years' time, you will find it in a hospital in Szeged. So that's pretty much one of the big problems that we are facing with. So what do we need? Well, there's a lot to do, quite honestly. We need new antibiotics, that's for sure, but what type of antibiotics we need? There has been some major claims that some antibiotics may be resistance-proof, e.g. saying that resistance against these bacteria, against these drugs will unlikely to happen. And for example, there has been one paper, I think a year ago. It's an enormously exciting paper with the title, "A New Antibiotic Kills Pathogens Without Any Detectable Resistance." Now, if you read the paper, you will find out that it's amazing protocol how they find these new antibiotics, and it's clearly effective against some of the most dangerous pathogens. But when it comes to the way how to test, they tested resistance, whether it can arise de novo in the laboratory, the method they used were pretty inadequate. So I would put quite some money on that. If I had the money, if I had my hand on these very molecules, I can generate you antibiotic-resistant bacteria in a few months' time. So yeah, so what I'm actually trying to say here is that that's actually the other important goal. It's not just detecting, not just making new molecules, new antibiotics which would enter the market, but also in new diagnostic tools that will allow you to study the evolution of antibiotic resistance in the laboratory in a rapid and in a high throughput manner. When I just say that you happen to be interested in hundreds of molecules, which are all of them are promising, in terms of that they are effective against current drugs, they are not toxic, etc., etc. Which one to choose? Which one to actually you have to concentrate on? Well, it would be really nice to have a tool that would give you an estimate how rapidly evolution of resistance would emerge if these molecules enter the market. And this is actually one of the things we do. And thirdly, we need new diagnostic tools, we need new antibiotics, but as a matter of fact, there are new antibiotic policies that must be done, and it's really the responsibility of the governments. Let's just say when exactly in a clinic you have to use certain antibiotics, and when it is right to use, and when you have to minimize the usage of antibiotics. And the reason being, and this is a good news, that antibiotic resistance is costly in terms that when such mutations or such plasmids arise, and usually the resistant bacteria actually have a slower growth rate, so they can divide much less rapidly as the sensitive counterpart. So if we reduce the dosage, in certain cases, they will actually eliminate it by the sensitive counterparts. And this has been shown in quite a few hospitals, especially in Sweden. This is true for certain drugs, but not for others. And for us as researchers, one of the responsibilities is to demonstrate which are the best treatment for the hospitals, when to use antibiotics, and what is actually the best protocol for antibiotic usage in the long term. Right, the last thing I'm actually pretty excited on is antibiotic combinations. One reason why resistance emerges at such an alarmingly high rate is because usually just one or two mutations and that's it. Because they actually the antibiotics only usually have one target within the cell. And if this target mutates, and that was it, resistance emerges. So what we really need is drugs that have multiple targets. If you say, they may be called dirty drugs, if you like, that have multiple targets or combination of drugs that will attack at numerous different places of the bacteria, and therefore resistant bacteria that are simultaneously resistant to multiple drugs will be most likely to be achieved. or they would need much longer time. So this is one thing we are actually focusing on, but finding the right antibiotic combination, if you like drug cocktails, it's an enormous task and difficult one. Now, if you happen to be interested in what we actually do and what we have achieved within this area, please visit our website or follow us on Facebook. Thank you very much.